As you see, as I told very shortly, the 800.11e standard will give the new method of block acknowledgements. There you can acknowledge a bit mask of every frame you have transmitted here, and there. And so, when only one frame is corrupted, you will only retransmit this frame, but not all. So this is actually not the real problem for more the increased delay. But if you have a very noisy link, you will run into really troubles, because the block acknowledgement, at least at 100.11e, is still a lot of overhead. At 100.11n, it's a bit better. You have no separate packet. They can be included in the normal Wi-Fi header. So, yes, this won't you? It's quite okay. Further questions? Okay. Okay, half an hour passed. Let's go on. A bit slower. Okay, as I told you, the assumptions taken in the Wi-Fi standard does not really reflect two-user scenario on a point-to-point link, and also not really the situation on a mesh network when you use a shared channel. So at least the collision avoidance and the quality of service techniques look like as if we could get some performance out of these by optimizing the values. The first one, perhaps the interframe space. This is the access delay in front of every medium access. It should be quite easy to optimize this. Just make it really small, because there's no use for traffic differentiation on a point-to-point link. You cannot do it on higher layers or somewhere else. Okay, and this will save you at least one time slot. It's not much, but it is at least a bit. On a 54 megabit link of 100.11a, it's 2.45%. If you, it's perhaps 1 megabit. It's quite nice. This number will increase if you use a new standard of 800.11n. There it will be nearly 4%. This is because the time on the interframe spaces and the timeouts stay more or less the same in this standard, but this, you will send more data at the same time, especially with using MIMO techniques. You can send 4 streams of data at the same time. So the efficiency between the time you're actually sending and the time you're waiting on your medium goes dramatically down. And so even this one very small time slot can give you an impressive performance increase. Using 4 streams at 800.11n will give you 5.25%. This is, I think, it's beginning to get interesting. As I told you, the CW max value, you can set it just to the CW min value. It doesn't, it's not really needed on point-to-point links. So the first interesting part, the CW min and the TX op limit. Both can be optimized, and when you optimize both, here you see the CW min value. It's always calculated 2 to the power of n minus 1. So you have always powers of 2 in the range of your random numbers. You can have 2 to the power of 1 or 2 or 3 or 4, resulting in a range between 0 and 8 minus 1, and or 0 to 16 minus 1, and so on. On the other side, here are the different times for the TX op limit. It's just in seconds or in microseconds. Oh, I think you cannot read the numbers. Even I can't read them. Let's look at the PowerBook. First, we don't use any optimization. When we just use the 800.11e parameters like the normal standard of 100.11a, b, or g. The throughput you can see here is not really great, but you will see if you use longer times for the transmission opportunity, the throughput will increase. But it won't increase until the maximum value of the TX op limit. Somewhere it's an optimal point, and afterward the transmission, the throughput will decrease again. This is mainly a consequence of the semi-min value, because wait, just another slide. It's also dependent on the distance of your link. The throughput, if you have longer links, you have to adapt the time slots and the interframe spaces, and the result will you just see on this both slides. The graph will change a bit, and the optimal points of throughput will also change. When it was, for example, on the short range link at a min value of 3, and as you see here, let's choose perhaps this green line. It's at a min value of 3 and TX op limit of 2 milliseconds. You see an optimal point, a maximum there. On a longer link, this will change. The optimal time for the TX op limit will here be at 4 milliseconds. As you can see, it's quite complicated to find the optimal point or the maximum for all this. This is because when you have a long TX op limit, both stations will access the media for a long time. And the CV-min value will give you the probability of a collision. There could be a collision somewhere, and at this point, both sides will both lose the data, because both are sending, and at this point, no one will hear the other side. If you have a long TX op limit, you will lose a lot of data. If you have a short TX op limit, you will lose only a few data. So it's clear, if you have a really long TX op limit, you should increase the CV-min value to decrease the probability of a collision, because when then a collision will occur, you will lose a lot of data. So if you just choose on this graph some points, if you look at this is normal 800.11g or a, really unoptimized. If you now find the optimal point in this diagram, perhaps will be this line at CV-min value of 4 and transmission opportunity of 4 milliseconds, you will see it's a quite big number at nearly 15% more throughput. That the increase of delay, it's up to you if you can live with this optimal number, 4 milliseconds. If both access the channel, you will actually have a delay of 8 milliseconds. I think for normal operations it's still a good time. And okay, wrong. wrong. The first number is optimization between when TX-op limit is 0. It's this bar compared to that bar. When you just change the CVmin value and let the TX-op limit time stay the same. So you can see a 15% increase, and if you do an overall optimization from there to there, you will even get nearly 30% more throughput, and the delay is still acceptable, at least I think. This is nice. This was UDP. Using TCP is quite more interesting. If you just do some stupid TCP tests, not using UDP, just replacing the protocol, you will see the throughput is nearly 25% behind UDP. That's interesting, but we will remember, as I told earlier, it's a problem with the delay spread on this Wi-Fi channel. And the problem with the round-trip time, I have to speed up a bit because the time is running. Okay, the first idea how to solve this, okay, use another channel, use it like the normal Ethernet, build a full duplex point-to-point channel using two separate channels, one for upstream, one for downstream. This actually will increase the amount of hardware you will need and the amount of spectrum to the double. As you can see here, a small test bed. We can see here two hosts communicating with each other, a router for separation the traffic flow from host 1 to host 2, and host 2 to host 1. You could imagine the traffic will flow there, and backwards it will flow there. It's quite easy. It was implemented using normal Linux and Cypress PCs with Atheros cards, at least the cards you understand 800.11a. As I told you, this will double the performance. Okay, nothing special. It will also solve the contention on the Wi-Fi link. Okay, nice, but what will mean this? And it will open the door for some optimizations. Okay. So you're now alone on your medium. Every node can more or less send at every time they want. So you can reduce the CVmin value to a minimum. What is a minimum is a bit a problem. If you do it with Atheros, you cannot set it really to 0 or 1, because then the Wi-Fi card will restart every time. I don't know if this is a bug or a bug in the hardware abstraction layer or something else. It's just occurred, and I don't know why this happens. But in theory, you even could this value to 0. The TX-op limit in the standard has a maximum of 8 milliseconds, and you can set this to the maximum. Okay, using an unidirectional TCP stream. As you can see in this graph, this is the normal one channel using with 2 users and used in a shared way. You have, as you can see, again, this optimal point of here for TCP and TX-op limit of 1 millisecond and a CVmin value of 4. It's quite slow compared to the other bars. This is the throughput you can get on the forward connection of a TCP stream when you use a separate channel for forward and backward connections.